See, ethers are of two kinds, symmetrical and unsymmetrical. If both sides the alkyl groups are same, we call it symmetrical. For example, this is a symmetrical ether. The name of that is dimethyl ether, which is a common name. Methoxymethane, which is a IUPAC name. Okay.
Yeah.
This is an unsymmetrical ether. You'll always read methoxy as a substituent group. So that will be methoxyethane. Okay. Common name is ethyl methyl ether. If you have this kind with oxygen and methyl, you will call this as methoxy propane, but at which position? 2 position. So 2-methoxypropane. If you have this one, this is methoxybenzene and it has a common name known as anisole. This is ethoxybenzene, common name is phenetol. If you have a cyclic 3-membered ring ether, it is called epoxy ether. Okay. PIN means preferred IUPAC name. SIN means strict IUPAC name. Okay. So this was supposed to be the IUPAC name. Nowadays, this is more preferred. So oxirane is what you will write it as the IUPAC name. And this is ethylene oxide. This is a common name. Okay. Numbering should always start from oxygen. And you see that 1, 2, 3, the IUPAC name given is 2-methyl-oxirane. Okay. And this will become 2-ethyl 3-methyl-oxirane. Okay. And here it will become 2,2-dimethyl 3-ethyl-oxirane. Is this clear? Right. Just like 3-membered ring is oxirane, 4-membered ring is oxetane, 5-membered ring is oxolane, 6-membered ring is oxane. Okay. Usually this one and this one are more commonly used and asked. This is called 1,4-dioxane because this is also a 6-membered ring, but it has 1, 2, 3, 4. At 1 and 4 position we have oxygen. That's why we call it as 1,4-dioxane. Okay. Normally, if you notice the structures of alcohol versus the ether, ethers usually have a larger bond angle because of the steric repulsions between methyl groups. Got it? That way, it will try to have a lower dipole moment, which affects on their boiling points. So these are few boiling points given just to understand how water suddenly is 100 degrees, but same dimethyl ether is minus 25 degrees. So I can see without hydrogen bonding, there is a drastic difference in the boiling point. Okay. And this is just for the information's sake. Now, all these reactions we have read as the chemical reactions of alcohols. Okay. So you can see if you have an alkoxide, sodium alkoxide, it could be a 1 degree, 2 degree, 3 degree benzyl vinyl allyl, any form of alkoxide. But this side it should react with alkyl halide, which is SN2 ready. SN2 ready means it has to be either methyl, 1 degree, allyl, benzyl, only these kind. These are called as SN2 ready. So if you have SN2 ready, then RO minus will attack here, X minus will be left. So that gives us RO R dash. Okay. With NaX here. Clear?
Yes, sir.
So this is Williamson synthesis. And now you notice 1 degree alkyl halide with 3 degree or more carbon gives E2. So suppose if this was 3 degree, it would always give you E2 mechanism. Okay.
Yeah.
If you have 2 moles of alkyl halide, then you react with Na2O or dry Ag2O. So first Rx will be attacked by O2 minus, X minus is removed, that will become RO minus. So that will react on the second mole of Rx, removing X, and that's how you will get an ether form. Okay. Sorry, beta, check. From alcohols, if I take something like ethanol treated with concentrated H2SO4, maintaining it less than 413 kelvins, then you will get ethers. If it crosses beyond 413 kelvins, you will get alkenes. We have discussed this in alcohols also.
Yeah.
Same thing, if Al2O3 is around 250 degrees ethers, 350 degrees it is alkenes. Okay.
Okay.
If I take sodium, sodium will take H plus away, RO minus will attack. This is typical Williamson synthesis. If I take diazomethane, CH2 minus will take H plus away, RO minus will back attack, remove N2 gas, you will get methoxyalkane. And this also I told you, with OH minus H plus is removed, RO minus will attack on methyl, sulfate will come out, you will get ethers.
Yes.
The same logic can be applied for phenols also, and you will get methoxy benzene, which is anisole. Okay, these are all anisoles. Okay, in case if you have an alkene with oxymercuration, first you will get a mercury bridge, and methanol, instead of water we are taking methanol, so methanol will attack, this bond will break, and thereafter H minus will come here and attach. So that's how you will get methoxyalkane. Okay, logic is the same. Oxymercuration, demercuration. Same way, instead of using water, if at all I to use methanol in acidic medium, first pi bond will take H plus, carbocation will form, methanol will attack here. That's how you will get methoxyalkane. Okay. MCPBA will, this is a peroxy linkage. So peroxy group will go with oxygen, it get linked on both ends. So you will get a epoxy alkene, or simply we call it as oxirane. Ag2O and heat will also give you oxirane form like this. Okay. So these are all something which we have discussed as a part of pi bond reactions as well. From halohydrin, suppose if you have a chlorine and OH at vicinal positions, OH minus will take H plus from here, creates O minus, and that O minus can internally push, remove Cl minus, and that's how epoxide can be formed. It can also be done whenever it is a trans position in a cyclohexane group. So H plus can be removed from here. O minus can internally attack from the bottom, remove chlorine, you will get this epoxy ring. Okay. But by chance, if it is not in a trans position, then OH does not accept this H plus because it is not going to lead any product. That's why OH directly attacks here, removing out this chlorine. So you will get diols. Okay.
Okay.
If sodium or NaOH is taken, wherein bromine and OH are present in the same structure, OH minus can take H plus, O minus can attack, remove out this bromine. That's how you will get again an ether form. Okay. Clear?
Yes,
And
sir.
even if you have OH minus can take H plus from here, and this O minus has to attack, make a back attack, remove this bromine here. Correct? So can I say this is like an erythro form because both the groups are on the same side, and I'm making a back attack. Back attack means anti-attack. Correct? If it is an anti-attack, what should be the product here? It should be trans, right? So in a cyclic structure, how do I show trans beta? Keeping the groups opposite to each other. So you can see
Yeah.
this methyl and methyl are opposite to each other. That makes it trans. Clear? Okay. This is just to show you how the mechanism is worked out.
Yeah.
Same way OH minus can take H plus from here. O minus can attack. Remove here. You'll get oxetane or oxolane. Okay.
Yes, sir.
Ethers typically have a lower dipole moment. Okay. And because of the hydrogen bonding, ethanol will always dominate over the ethers. Generally, it is used as a solvent as they are sufficiently volatile and unreactive. Lower
Okay.
ethers are soluble in water. For example, if you take methoxymethane, methoxyethane, ethoxyethane, up to this there is a decent solubility in water. But as this R group keeps growing, solubility starts decreasing. Okay.
Okay.
Typically, there are two reactions that are observed in ethers. One is an acidic hydrolysis. The other one is reaction with acids directly. For example, if at all I take ROR in water, which is maintaining a pH as 7, you will not see any kind of reactions here. So in fact, ethers are stable in water, they do not make any reaction. But if at all you take basic medium, you know that this oxygen is containing lone pair, and again you are trying to push a lone pair group, so that does not make any reaction either. So here also in basic medium there is no reaction. So which means whether you keep the pH 7 or greater than 7, you'll hardly see any reactions happening. So ethers
Okay.
will only react in acidic medium. Okay. So if the pH is less than 7, then the oxygen can get protonated, take H plus, and try to make one of the group as leaving group. Either this side it will become alcohol and becomes a leaving group, or this side it will become an alcohol and a leaving group. Okay. And to leave that, some nucleophile has to attack, right? So the nucleophile can attack here or here, and it can proceed via SN1 or SN2 mechanism. Okay. Now, because in basic group there is no reaction at all, we can say ethers are quite stable in basic medium. That's why if at all you directly push any nucleophile without making an acidic addition, like OH minus Cl minus Cl minus F minus, anything you push towards ether, there is no reaction that will happen. Okay. That's why ethers are taken always as solvents in this case. You have noticed PCl5,
Yeah.
PCl3, SaCl2. For those kind of SN2 reactions, we always take ethers as the solvent. Okay. Because nucleophile cannot react with ethers. So it has to go for other substitution. Clear?
Yes, sir.
Now notice, first reaction is hydrolysis of ethers. So first I need to put acidic medium. But if at all I have a cold concentrated H2SO4, it will form this kind of adduct and further reaction is not observed. Got it?
Yeah.
Like a salt. It is like a salt, and that is where it will end. But if at all you take a dilute condition can be given this way: H plus in water, H3O plus, dilute H plus, dilute H2SO4. These are different ways of representation. Okay. In that case, oxygen will first take H plus, convert into this ion, which is called as oxonium ion. Now, here is the interesting part. If either this R or this R, okay, any of these R is 2 degree, 3 degree allyl, benzyl, OCC related carbocation or aromatic form of carbocation is possibility to form. If any of these is a possibility to form on any of these two sides, then the reaction will always go via SN1 route. Okay.
Okay.
But if both sides of this R, we have only methyl or only 1 degree, in that case, it has to choose SN2 route. Got it? If it goes via SN1 route, mechanism typically happens this way. First, an oxonium ion is formed. Bond from one side will break. It will break towards the more stable carbocation. Thereafter, water will attack and this will form alcohol. So, end product is two alcohols. Okay. SN2, without forming a carbocation, direct attack, direct removal, both will happen simultaneously. You will get alcohol and alcohol here. Okay.
Yes,
Let
sir.
me show you examples. If both side we have methyl, obviously first H plus is been taken, oxonium ion is formed. And since both side we have methyl, SN2 reaction is favorable. So water will attack here. Simultaneously, this bond will break. So you'll get 2 moles of methanol. Okay. But if you have this molecule, first protonation will take place here. And then the bond will break here because this will lead to a stable carbocation. And once you get a stable carbocation, then water molecule will attack, thus giving a 3 degree alcohol. So if this oxygen was an isotopic oxygen, it will end up going with methyl group. And this is the oxygen coming from the solvent water. Okay.
Okay.
Is the first two cases clear?
Yes, sir.
Check out the third case in a similar way. This is a 2-degree carbon. This side is a 1-degree carbon. So definitely after protonation, hydronium ion will be formed. And like I said, if there is either 2-degree, 3-degree and above, you'll always go via SN1 route. So this side of the bond will break, carbocation will form here, and water will attack here. So that's why this carbocation attacking with water, you will get this alcohol. Okay. Now here you see, this is methyl, this is ethyl. So there is no 2-degree at all. So it will favor SN2. But first, after protonation, you need to check out which side is less substituted. This carbon is less substituted because SN2 always happens in the direction where it is less substituted. So then water will attack from here. The bond will break onto this side, makes it ethanol and methanol. Okay.
Okay.
This side also you can see it is 1-degree and 1-degree. So again it will favor SN2. First protonation will take place, and after protonation, water will attack simultaneously on the less substituted side, which is this one. Bond will break onto this side. Okay. Clear? That is
Yes,
what I
sir.
have shown it here. Correct. There's an extra page. I'll just delete it. It's not relevant here. Right. See the next one. If there is one side phenyl and other side is there, then phenyl side there is always a double bond character, because you notice that when you have oxygen here like this, oxygen is connected with CH2, CH3. This is the structure. Then obviously the lone pair of oxygen is always in resonance with the benzene group here, isn't it? So that's why bond breaking on this side will be very difficult. Okay. So bond will always break on the other side only. Now you need to decide on other side what kind of a group it is. It is 1-degree, 2-degree or 3-degree. So since it is 1-degree, you'll go for SN2. So water will attack here. Bond will break on this side. So you'll get phenol and ethanol. Okay. Next one. This side is 1-degree, but this side it is 1-degree allyl. And like I said, if there is an allyl group, definitely you have to go for SN1. So first protonation will happen like this, and bond will break here, makes a carbocation here, then water will attack on this position. So this carbocation will take water and you will get this product. Okay.
Okay.
Next here also, left side is 1-degree, right side is 1-degree, but this is benzyl. So benzyl is also very stable carbocation. So it will form SN1 it will go via SN1 mechanism. Hydrolysis will happen to get this alcohol. Okay.
Yes, sir.
Now notice this side. This is very interesting part. Left side is 1-degree, right side is also 1-degree. Right side is bulkier, but still the oxygen connecting carbons are 1-degree. So that means it will still favor SN2. So the attack of water will always be here. Bond will break on this side. So these are the products which you will get. Now notice if both side phenyl are there, or phenyl and cyclopropyl are there, or phenyl and this kind of tert butyl group are there, wherein SN2 is not possible, and here carbocation cannot form, neither SN2 can happen, and here also neither SN2, I mean, actually this got repeated, but this was with this side now. Okay. So in all of these cases, neither SN1 nor SN2 is favorable. Hence, they will not go any hydrolysis reactions. Okay.
Okay.
Right. Same is the cases for 15 and 16. Now 17 is a very interesting one. Check out. If imagine one side is vinyl, the other side is, simple 1-degree, 2-degree, anything, any group it is. Then if you do hydrolysis, you always need to break on the vinyl side. Remember it like a shortcut. See, you break it on the vinyl side, giving OH on the double bond side and H on the oxygen side. Okay. And if you do so, what do I get? I'll get CH2 OH group here, and that will tautomerize to form aldehyde. And this side you will get an alcohol. Okay, clear it up? This is a shortcut to remember. Now let us understand how does this happen. See, in the mechanism, because at the vinylic position, oxygen will always favor resonance. Okay, so now when the H plus approaches, since this lone pair is involved or busy in resonance, the carbon from here will attack the H plus first. So it will become CH3, and there is a partial, double bond character with oxygen getting positive charge. So first water will attack on this carbon because pi bond can shift on to oxygen. Okay. And internally, this oxygen can take H plus here, convert itself into OH plus. And now this becomes a good leaving group. So to push this group away, the lone pair from here will push here, remove this ethanol, and thereby this will become an aldehyde form. Okay, so please go through it once carefully. You can see a shortcut. I have written it at the bottom. You can see the same thing. Okay. Finished?
Yes, sir.
So you can see these following examples, 18, 19, 20. What we are doing? We are just using the shortcut. This is a vinyl side. Break it, give OH on the left, H on the right. So you'll get this enol, convert that enol into ketone. Okay. Next one. This is vinyl side. Break it, give OH on the left hand side, H on the right hand side. This is enol, convert into ketone. Here same. This is double bond, break it, OH on the left, H on the right. So this is enol, convert into ketone. Done? Right. Now let us understand what is acetal and hemiacetal, how the hydrolysis happens for them. Hmm. Acetal is a ether group wherein it is a geminal ether form. That means on the same carbon you have two OR groups. Okay, that is called acetal. If one of the group is OH and the other group is OR, you call it as hemiacetal. Okay, beta. So one is acetal, the other one is hemiacetal. Okay, and
Yes, sir.
now if you hydrolyze the acetal group, then this part will convert into aldehyde, and these two parts will come out as 2 moles of alcohols. Again, that is a shortcut. Okay,
Yeah.
I'll show the mechanism, but shortcut is you break on both sides, give OH on the left hand side 2 times, and give H on the right hand side 2 times. That's it. Okay, so that way left hand side, if carbon has 2 OH groups, that will convert into an aldehyde. Hmm? Same way, even if there is a hemiacetal, you do the same thing. You break it on both sides here. This side you'll get OH and OH. This side you'll get H and H. So one will become water, one will become alcohol, the other one will become aldehyde. So you got the idea of shortcut, how to use it. Now
Yeah.
see the mechanism, how it happens. See, if there is an acetal, the lone pair from this oxygen will attack H plus. You will get this as ROH. And ROH is a good leaving group. So the lone pair from here will push to make this group come out. Then you will have a double bond character here. On that, water will attack, pi bond will again move on oxygen. You will get this as OH, right? OH2 plus has been done. So lone pair from this oxygen will internally take away H plus, becomes ROH. And now the lone pair from oxygen will push so that this ROH can leave, thus giving away aldehyde and alcohol form. Okay,
Okay.
one second. right? Check out these respective examples now. This is hemiacetal, hemiacetal, hemiacetal. What did I do? I just need to break it. Break here, OH on the left, H on the right. Break here, OH on the left, H on the right. Break here, OH on the left, H on the right. So this part will become aldehyde. This part will become alcoholic part. So you can see this will become aldehyde. Then we have phenol. This side will get aldehyde. This side methanol. This side will get aldehyde. This side alcohol, ethanol. But are clear?
Yes, sir.
Okay. Next. In case if you have OH and PO minus here, PHO, again you break it here. I mean, this is the same reactions which I have done it. So check out. Next, if by chance there is a cyclic ketal given, what is cyclic ketal? Suppose on a ketone group, if alcohols from the same molecule, 2 moles of molecules are combining here, then this is also an acetal form, but this is a cyclic acetal. But if it is coming from ketone, you can call it a cyclic ketal. Okay. Cyclic acetal or cyclic ketal is a common wording used here. Okay.
Okay.
Now see this carbon. This carbon has one oxygen on the left, one oxygen on the right. So you can easily break here and here, give H to this oxygen, give H to this oxygen. Correct? And at the center, you can get two OH groups. You can see center, you can get two OH groups. Two OH groups will convert into an aldehyde form. And this part will convert into a methanol form. Okay?
Yes, sir.
Right. Next. Again, if you do hydrolysis here, you have to break this side. This side you will get OH, this side you will get H. So this carbon having two OH groups will convert into aldehyde. Left hand side you will have alcohol. This is the part which will have alcohol. Okay. So here also it is cyclic acetal. Break and break here. The center carbon will become aldehyde. Left and right carbons will become alcohol. Logic goes the same here also. You break it. Central carbon will become ketone. This side and this side will have alcoholic group. Okay. Here also break it on this side. The central carbon will become aldehyde, which is 1 mole. I mean, which one carbon, and the rest of this entire group will become alcohol. Now, if you have 3 carbons connected together, here, here, and here, all 3 are hemiacetal carbons. So break here, 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 and here, here. So these 3 carbons will become aldehyde, and remaining part is nothing but oxygen only. So which is this one? Okay, you'll get this 3 moles of aldehydes. Okay, clear, beta?
Yes.
Right. Okay. Next is, how does the reaction happen with HI? Okay. So when it comes to HCl and HBr, directly if you take concentrated HCl or concentrated HBr, reactions are very slow and backward reactions. Got it? So that's why reactions are typically observed with HI only. It has to be an extremely strong acid. So therefore, with concentrated HI, first the lone pair will take H plus, converts into this oxonium ion. And then I minus, which is a strong nucleophile, will attack on this R, breaking this bond. So you'll get one part as an alcohol, the other part as an alkyl iodide. Okay. But whether it favors SN2 or whether it favors SN1, that depends upon what type of R group we have. Now notice, if left or right side of the alkyl group, any one of them is 3 degree or benzyl or allyl, then it will favor SN1. Okay. But
Yes.
if both of them are either 1 degree or one is 1 degree and the other one is 2 degree, in that case SN2 is favorable. Okay.
Okay.
Now notice this case. First, in this case, first protonation will take place. Oxonium ion will form. Okay. And after that, I minus will attack. Clear? One second. See. So here I minus will attack on CH3. This bond will break. So you'll get 1 mole of methanol and 1 mole of CH3I. Okay.
Hmm.
Again with concentrated HI, lone pair will take H plus, gets this oxonium ion. Of course, left hand side and right hand side, both of them are 1 degree. So I minus will attack on the less substituted side, which is CH3 here. So that makes it SN2 reaction. Okay.
Yes,
And
sir.
next, if the lone pair takes H plus from HI and thereafter I minus attacks on this position, because again it will favor SN2 because left hand side is 1 degree, right side is 2 degree. Correct. So then SN2 is favorable and I minus will always attack on less substituted carbon. But now notice this one. Left hand side is 1 degree or methyl, but right hand side is 3 degree. So I told you, like, the minute you start growing up 3 degree or phenyl, benzyl or allyl, it will always go via SN1 mechanism.
Yes.
So first protonation will happen, bond has to be uh, broken here, and you'll get methanol, and this part will convert into an carbocation. Thereafter I minus will connect and you'll get this iodide. Okay. And next,
Okay.
here also same logic. In fact, you know that on phenyl side we can never break it, so you will have to break it on this side only. Phenol will separate out and then this side will convert into carbocation. I minus will attack and you'll get iodide. Now this side again, we cannot break it on the phenyl group side here. This bond cannot be broken. So O and H protonation will happen here. I minus will attack on this carbon. Bond will break here, right? So and it goes via SN2 mechanism. Now this time you can see left hand side there is benzyl. Right side, although it is 1 degree, left hand side is benzyl. So it will favor SN1. So first protonation will take place. Bond will break onto this side. The arrow got wrong. So bond will break onto this side so that we can get carbocation. And then I minus can attack. You'll get this product. Okay. Just like above how the hydrolysis was not possible, same logic if you have two phenyls, one phenyl and what do you say, one phenyl and bicyclo ring or two bicyclo rings, in these cases no reaction observed.
Okay.
Second case is if HI is in excess. If HI is in excess, then what you will do? If HI is in excess, first protonation will take place. Then you will follow the usual mechanism, whether it is SN1 or SN2. But
Yeah.
once you get an alcohol, right, you convert that alcohol also into iodide because you have excess of HI. So you protonate that alcohol again. Sorry, here protonate that alcohol again and get this as a water part, and then I minus has to be attacked again to get alkyl iodide. Okay.
Yes, sir.
Right. So you can see this side and this side I can break it. Left hand side I can have iodide, right hand side I can have iodide. So 2 moles of alkyl iodide can be formed. Okay. Next. Same logic here also, if you have excess, first you'll get an alcohol and that alcohol also need to be converted into iodide. Here also break both of them, you'll get both the iodides. Short. If you have excess, you don't have to think so much. No, you just have to break it. Both sides you have to distribute iodides. Okay.
Okay.
But if you have a phenyl, even though you give excess, you cannot break this bond, right? So that you have to leave it always as a phenolic group. You cannot get it as a iodide form there. Clear?
Yes, sir.
Right. So therefore, only one iodide will form, other one will remain as phenol. Okay. Third case is, by chance, instead of giving uh, concentrated HI, he has mentioned anhydrous HI. Okay. Well, how much is the difference concentrated HI and anhydrous is that concentrated HI may have small composition of water. Here there is no water at all. In that case, if there is no water, SN1 is not at all favored. Everything is favored via SN2 only. Okay. For example, if you have this case, and if I take anhydrous HI, first protonation will take place. Thereafter, I minus will directly attack here, breaking this bond. It happens via SN2. Clear?
Okay.
Here also, if you have anhydrous Hi, I minus first protonation will take place, then I minus will attack here, breaking this bond. Obviously, if you have this group or this group, because SN1 is not possible, even if you have 3-degree carbocation here, since carbocation is not able to form, this reaction will not proceed. Correct? So this is a way to remember in which case what to be taken. Clear?
Yes, sir.
I have given you some exercise questions to work it out to see, whether you can get the product correct or not. Okay. Suppose if you have a methoxy groups on, something like a phenyl ring or anything. Okay. And I need to find out how many number of, moles of Hi are required to overall remove this methyl. Okay. Then what you can do? You know that protonation will happen here also, protonation will happen here also, then I minus can attack here, I minus can attack here. So you will get this, uh, catechol. This is called catechol, and then we have 2 moles of methyl iodide. Can we convert this into iodide? No, right? So that means you will stop the reaction here. So what is the value of X here, beta? 2. So you cannot consume more than 2 moles of Hi. Clear?
Yes,
Same
sir.
way, here we can have, there is a phenyl group here. So obviously here I cannot make any reaction. So again, only here I can use 2 moles of Hi. So again, X is 2 in this case also. Okay.
Yeah.
Next. Imagine if this side there is a methoxy group, this side there is a methoxy group. Then how many Hi are required? See, first protonation will happen here. Protonation will happen here. One iodide will attack here. One iodide will attack here. So how many are done? 2 moles done. So in 2 moles, methyl iodide has come. Now then you get an alcohol, right? You get glycol here. So you'll get OH and OH. And again you need to protonate them like this. And 2 more iodide has to be attacked here. Correct? So 2 more iodides will make it as, vicinal iodides. Okay. And we learned that vicinal iodides are unstable. So again, it will come out as alkene. So on alkene, again, I can add Hi. So finally, you'll get this as ethyl iodide. So how many moles we consume? Here I consume 2 moles. Initially, I consumed 2 moles to get these two. And lastly, I got 1 more Hi. So how many moles total? 5 moles. Okay. It's a very standard JE question. You need to be figuring out how many number of Hi are required. Same way. If at all I protonate here and here, I minus will attack here, I minus will attack here, break this out. I'll get catechol and vicinal iodides. Vicinal iodides are unstable, you'll get double bond. Again, 1 more Hi can be added. So total 3. And if both side we have phenyl groups, no reaction, so X is 0. Got it?
Yes, sir.
And lastly, if you have this side with OCH3 and OCH3, first 2 moles to remove this into iodide form, and you get an alcohol here, alcohol here. This is not a phenyl group. So again, these alcohols can be removed with 2 more iodides. So you get iodide, and 2 iodides are unstable, double bond will form here. And 1 more Hi will get added. So finally, you will get iodocyclohexane. Okay. If you have this
So,
case, 3-methoxy, you will get 8 of them. Yes, beta.
so I'm not feeling well. Can we end class a little early today?
Yes, beta.
Okay.
Sure. See, last thing, we'll figure it. This is the last part we'll discuss, and then we'll wind up. Okay.
Okay, sir. Thank
Zichel's method. What is Zichel's method? It is used to figure out how many methoxy groups are there on the phenolic ether. So first what we say, let's say there are 3 methoxy groups. So I'm using excess of Hi. So definitely I'll get 3 moles of ethyl iodide. 1, 2, 3. 3 moles of methyl iodide. Then you react with AgNO3 and heat. So all of these iodide will get attached with, combine with silver to form 3 moles of AgI. And this is a precipitate, so you wash it, dry it, then weigh it. Let's say the weight is X grams and the original weight of this compound is W grams. Okay. So how many number of moles you will have? W by M is the number of moles, correct?
Yeah.
Isn't it? And those number of moles, let's say if you have N number of methoxy groups, so that N times of number of moles will give you total number of methoxy groups. And that total number of methoxy groups should match with the total number of AgI, correct?
Okay.
So therefore, this weight divided by molar mass, that should map with this one. So using this quantity, X is given, W is given, molar mass will be given to you. You have to calculate what is N. Clear? So that's how we can figure out what is the number of methoxy groups.
So, how do you wash or precipitate? Like wash and dry?
So if you have a solution like this with some precipitate down here, clear? First you will filtrate it, correct? All the liquid will drip out, just like a normal filter, how we do that, clear? Then
Yeah.
we put it on the, absorbent paper, filter paper, clear? Okay. And from the top, we will start giving away sufficient heat so that the moisture will be evaporated slowly. So leftover will be dry precipitate mass. Okay.
Oh, okay.
Clear, beta?
Yes, sir.
Right. Okay. So this is all the reactions of ethers. Last reaction is about how it reacts with air. Okay. With air, basically at this alpha position of oxygen, you will get a peroxy linkage. Okay, but this is a very slow process. Correct. Okay, usually with oxygen, you'll see here we'll get OO getting inserted between carbon and hydrogen bonds. Okay.
Yeah.
And this insertion will make a hydroperoxide, and hydroperoxide is usually explosive in nature. That's why ethers are always stored in dry bottles, so that it is not much exposed to the light. Otherwise, it will start forming radical and it might start become explosive. So in case if I take chlorine in a dark condition, you might get a less amount of chlorination, but yet you will see at least one chlorine get attached. But if you take in excess, all the hydrogens will be replaced by chlorine, and this is the product you will get. Clear?
Yes, sir.
Ethers are identified in a very simple way, right? First, you convert ethers into hydrogen peroxy group like this. Okay, add some oxygen, leave it for some time, it will start forming hydrogen peroxide, correct? Hydroperoxide group. And then treat with FeSO4, adding with potassium thiocyanate. Here, Fe plus 2 in the presence of this hydroperoxide linkage will get oxidized to Fe plus 3. And Fe plus 3 forms a complex with SCN, which is a red blood color. Correct? So if the red blood color is forming, that means it is a presence of ethers. Okay, beta?
Yes,
The
sir.
same logic can be applied even if you take that hydrogen peroxide group, right? And then add it with Ki. Ki will convert into I2. It get oxidized to I2. And I2 will have a blue coloration in starch, right? And that's
Yeah.
a recognition that there is a ether that must be present. Done? Right? So that's it. This is the first part of, ethers. The second part is all about, using reactions all about epoxides. Clear? So that we'll discuss in the next session. Clear? So take some rest.
Yes.
Right.
So should we do an
1
extra
second.
class?